Fantastic. Good morning, everyone. Good afternoon, as the case may be, from those of you that might be joining from other jurisdictions across the world. My name is Andrew Beveridge. I'm the Chief Operating Officer with SmartSat, and I have the pleasure of welcoming you all to day one of the inaugural SmartSat Conference. In welcoming you here today, I would like to start with an acknowledgement of the traditional custodians of the lands and waters where we conduct our business, and we pay our respects to their elders past, present and emerging. The next 2 days is a packed conference program which will showcase SmartSat's first 2 years of operation and our future directions as well. While we would have enjoyed a face-to-face gathering with many of our colleagues, this was not to be this year. Nonetheless, we really felt it was important to bring the SmartSat community together in what we hope will be the first of several events like this over the life of SmartSat. Over the next 2 days, we'll hear from a number of our research leaders, some of our students and a number of our industry partners. They'll be presenting to over 270 delegates that have been able to join us online, which is a fantastic participation. So we thank you for you joining us. A couple of housekeeping matters before we get started, and I hand over to Carl I'll just do a little bit of housekeeping. So hopefully you'll have all received the full conference program. However, if you wanted to check timings, please head to the What's Next screen in the main auditorium. This will display in your local time. So whilst I'm here in Adelaide, Central Standard Time, what you see online is in your local time. We do encourage you to interact with the speakers using the live Q&A for each session. Session chairs will endeavour to get to your questions, but if not, I encourage you to reach out to colleagues via the online platform and virtual meeting rooms. If you've already had the opportunity to have a browse of the online platform, you'll have seen the poster hall. I encourage you to have a read of some of those posters, and thank you to all those that contributed posters to the event. We also have the exhibition, a number of SmartSat booths there. Booths are only live during the lunch break. So you can certainly access the brochures and view the content throughout the conference, but we will have people in attendance during the lunch breaks. Make sure you check your points that you're accumulating for the interactive with our speakers, visitors, booths, posters in the gamification section. There are some prizes up for grabs for our most active participants, and we'll be making some announcement on those on day 2. And to that end, I thought I'd introduce a bit of an icebreaker. Like you to participate in the first poll. We wanted to be able to maximise the use of this system. And early on in the conference, it's good to break down a few barriers and get people confident to push buttons and type questions. So hopefully this one is a safe enough poll. I was really keen to see what propels SmartSat. So I'll put this poll up. I encourage you to participate, become a little bit familiar with the system. I'll leave that up for a moment or two. Getting some votes in here now. That's looking good. I will share the results so hopefully people online can see what's happening. So what's really pleasing out of that is everyone's been very organised this morning. So that looks really good. So I'll pause that one now, end that one. Hopefully you're now familiar with the system and be able to be confident to type in questions and use future polls. So brilliant. Something between coffee and something but not coffee or toast seemed to be the winner of that one. Look, if for any reason you're having difficulties using the system or have technical issues, live support desk is available throughout the conference. So tap the button and engage the team. They'll be more than willing to help you out. Although this is a virtual event, we still encourage networking. The chat function enables you to reach out to other individuals or places you in rooms with new colleagues and partners. So make the most of the event. With housekeeping out of the way, I'll take this opportunity now to introduce our first session chair, and that is Carl Seubert. I'm sure many of you will be aware Carl joined SmartSat in May of this year as our Chief Research Officer. Carl returned to Australia after a career of some 9 years with NASA JPL as a senior aerospace engineer. He's a former graduate of the University of Sydney and went on to complete Masters of Science in Aerospace Engineering from the Missouri University of Science and Technology in US, and then a PhD in Aerospace Engineering from the University of Colorado Boulder. Look, it could be considered some of Carl's greatest achievements were associated with his time at NASA JPL and his contribution to the Europa Clipper mission and the next Mars lander mission. But for me, I probably think it's been a little bit more recent, and probably surviving 2 weeks in quarantine on his return to Sydney in a very small hotel room with a very young family. I think that is an achievement. So well done, Carl. Carl, it's great to have you joining us from Sydney today. I'll hand over to you to introduce our first speaker.
Thank you very much, Andrew. I appreciate that, and it's truly wonderful to be here. Good morning, everyone. I welcome everyone to, as Andrew said, our first SmartSat CRC conference. I'm going to go ahead and share some slides with you as we dive into this. So, as Andrew just mentioned, I'm Carl Seubert, the Chief Research Officer here at SmartSat CRC, and I'm joining you today, as Andrew said, from the suburbs of northern Sydney. This is the beautiful lands of the Garigal people of the Ku-ring-gai clan, and I pay my respects to them. I'm so pleased that you could all join us here virtually today for this conference. This will become a repeating and in-person event into the future. I did just return to Australia, and I'm starting to get more interaction with some of you. I very much look forward to expanding on that, particularly as our country opens up and actually coming out there, visiting your facilities, your labs, and really seeing in person the research and technology developments that we are doing together. We do have a really exciting and full agenda today over the next 2 days, sorry. We really do have an array of amazing projects that we're going to be presenting to you, speakers from both the SmartSat team, but also from our partners and yourselves across government, industry, and universities alike. Excuse me. So the objective of this conference is to really bring us together. This is a chance for us to introduce the SmartSat team themselves, give you an idea of our directions and where we're headed as a CRC. It's also an opportunity for all of us here to celebrate and showcase the achievements we've made together through our projects and our programs. But ultimately, this is really an opportunity to provide a platform for you, our partners, to present your research, your technology developments, and highlight the growth of Australia's space industry that we're already undertaking. And these research endeavours really are enabling the missions that will allow Australia to continue to reach further into space and become what we want to all become, a true spacefaring nation. I'm going to see if I can do this. There we go. So what I'm going to do now, I'd like to give you a quick snap perhaps of SmartSat. You're going to see a lot about SmartSat over the next 2 days, but this is just a quick snapshot. And I have to very much thank our excellent comm team at SmartSat, because they did the work for me here and putting together a great video that really captures, I think, the snapshot of SmartSat. So I'm really fortunate and happy that I can release this today and let you all see it. So I'm going to go ahead and show you just a very brief video. All right, it's extremely impressive what we've already achieved in the first 2 years of existence of the SmartSat CRC, particularly considering the challenge that have been placed upon us all during this pandemic. We really do have a great trajectory ahead of us though right now, and are really starting to build a lot of momentum in this research portfolio. And this is just an indication perhaps of some of the great things we're developing and really achieving here. I want to poke at some of these and just highlight some, and this is a snapshot of what's coming. You know, we've done a lot in the world of communications technologies, both in RF and optical, and you see some of that. We've really done a lot in Earth observation, in the sensing, the modeling, and a lot in the data analytics, and turning that into useful information that we can use at the end users to really impact communities and to get that in the hands of our management systems. We're looking at connectivity, IoT breakthroughs, and what we can do there. And most importantly, I think too, is where we're headed in terms of intelligence systems, in terms of payloads and systems, but also where we're headed in terms of autonomous and smarter spacecraft. And that's really what our namesake is all about. So there's a lot more detail to come over the coming days. I'm not going to dive any more deeper there. What I would like though, is to take this opportunity to talk a little bit more about the conference itself. You've all seen the agenda. If you head back out to the foyer, you can see what's coming up. A solid 2 days of activities. I want to just quickly thank the team behind this conference ahead of time. So we have, you know, behind the scenes, Jenny, Allison, Heather, Emily, and Elizabeth all really contributing and making this happen. So thank you. Thanks to all the SmartSat team and all of our partners. Day one is really going to focus on our PhD students, their projects, and what they're contributing as a part of the SmartSat team. And it's also an opportunity for them to network and engage, do their professional development, and really connect with industry here as well. And that's a key partnership we're trying to bolster here at SmartSat. And I think it's really important we work on that. So day two is really centered around building on that, and now where we're headed in terms of our overall direction, how that drives our projects, and where we will see a very good set of examples. Now, we couldn't show all of our projects. There's honestly too many, but we highlighted a few great ones that I think are worth bringing to attention. In advance, I again thank all of our presenters for being here over the next 2 days. I'm really excited to hear you speak and talk about your passion for research that you're undertaking. We do have this great host platform that we have here that we're going to continue to use over the next couple of days. It's very interactive. Take the opportunity to explore, as Andrew was mentioning before in the foyer. There's a whole handful of things. Interact here with other users. We also will have over the lunch sessions an opportunity to talk directly with some of our breakout sessions with some of our team there. These are just an informal way to actually dive in and have that networking opportunity. So please leverage on those as well. On top of the classic Q&A and the chats that we have here, that you've already featured the questions. I'm going to put up another question here, which is focused on the conference itself. So I'm going to go ahead and throw it out there. And I'd love to hear from you now, before we dive into 2 days of it, what you would ultimately like to take from this conference. So there's a quick Q&A there that you can go ahead and give me your votes. Let's see where we go. All right, learn about SmartSat. Networking, great. And this will not only perhaps shape where we're headed the next 2 days, but also where we're going with our future conferences, which is a big part of what SmartSat wants to do, and part of our overall strategy of engaging and bringing in our partners and our networks here. All right, everyone wants to learn about SmartSat. That's great. You'll hear plenty about SmartSat. So we'll go ahead and continue. Where we're going to head now is to our keynote speaker. It's my absolute pleasure here to introduce to you our keynote. This is Dr. James Garvin, who I'm confident you're all going to really find inspiring. His pursuits of space exploration are second to none. Jim was born in a blizzard, believe it or not, in Poughkeepsie, New York, and he was educated at Stanford, received his PhD in geological sciences from Brown University. Jim is a NASA lifer. He's at NASA, served there for over 37 years, and as a scientist in a variety of capacities. His current role is the chief scientist at NASA's flagship science center, which is NASA Goddard. He has over 100 publications to his name, has participated in more than 10 spaceflight missions as either co-investigator or PI. This includes the Mars InSight lander, as well as the MSL rover. He's flown experiments on the shuttle. He's worked with our partners, MDA, on Canada's RadarSat missions. And that's just to name a few. He'll dive a bit deeper. He served NASA headquarters as a special science advisor, and he plans new missions to explore the solar system. He orchestrates innovative scientific research. Jim has really done a lot. He's received multiple NASA Outstanding Leadership Awards for his work with Mars. He has 3 presidential rank awards for his scientific contributions to NASA. It truly is amazing. His passion for space exploration is evident if you go and watch some of his multiple TEDx speaking events. And on top of all of this, he's had a cameo in the film The World War Z, and he loves to travel to landscapes reminiscent of Mars and Venus, such as Iceland, and someday hopes to visit the new islands in Tonga. So currently, he's serving as the principal investigator for the newly selected Da Vinci mission, which is headed to Venus launching in 2029. This will return humanity to the Venus atmosphere to measure clues to its past ocean and how to understand exoplanets like Venus. I very much welcome Jim Garvin to wow us with your keynote speech. Thank you, Jim.
Well, thanks so much, everyone, for having me. I'm going to go to my video, and it's really a thrill to be talking with all of you because I lived in Australia as a kid and enjoyed it immensely. I still admit I didn't understand cricket, but forgive me for that. But maybe that I'll learn as part of our space exploration together. So what I'd like to do today is take you on a journey that's relevant to SmartSat because it extends how we explore space into new frontiers. And that's really what it's all about. The frontiers of understanding our home planet, protecting it, being aware of what's happening to it, planning the future of it, but also extending ourselves out into space. And so today, through the lens of a mission named for a great Renaissance visionary in many ways, Da Vinci, I'd like to take you into space through the lens of the planet Venus. And so bear with me as we go. And as Andrew said, I've been looking for Venus a long time. It's been over 40 years. That's embarrassing. Since the last US missions to the atmosphere. I worked with Soviet missions to Venus. Now, if you look at the bottom, you can see we're actually building spacecraft that can handle Venus conditions. So we can go there ourselves and bring the lab to the samples at Venus we want to study. And this is something that I think this current capability space we have in space research and technology will enable. So I'm thrilled to be here talking to all of you and to see Australia moving into space. And can't wait to visit and talk to you all in future time. So let me start the voyage. And the voyage I want to talk about today, and I hope is relevant to your conference, which is really that the engineering and technology solutions, those masterpieces that you all can develop, empower the science of the future. And we may start with science questions, life elsewhere, the state variables of Earth, workings of oceans, the universe. But in the end, the science goes through the master class, the master work of engineering and technology to enable us to extend ourselves into space and end up with the outcomes from science, which are the new knowledge and all of that. And today I'm going to use the lens of Venus. You can see the Curiosity rover there, of which I was one of the original founding fathers many years ago. But now we're talking about Venus and going back there ourselves, not with people, but with robotic craft, smart craft, to do that. So I'm going to take you on that journey at a very special time in space. And I think all of you at this conference are at the right place at the right time, because the business of space, how it engages with people everywhere, from Australia to the US to Europe to the moon eventually, is going to change. It's changing through frontiers of economics and knowledge, edutainment, and it's going to open up new frontiers. And not just the ones from science and the other traditional ones, but ones that engage us all as women go to the moon, as commerce goes to the moon, and as we expand our visions to places as bold as even Venus. So I want to talk about that today through the lens of science, but also from the technologies and engineering it will take to do that. But before I begin, I want to reflect for 1 minute. We're living at a special time because for over 30 years, that masterpiece of engineering has given us the new science, a foothold on the universe from the Hubble Space Telescope that dazzled far beyond its design life in a partnership between human spaceflight, technology, engineering, and science, working long beyond what anyone would have expected and producing this beautiful Halloween view of this magical universe that we're just getting to know scientifically. And what's coming next is even more exciting. Literally a cathedral to the stars with the James Webb Telescope that many of you may have worked on, that will engage billions of people as we look beyond what we can see into the infrared universe and attempt to understand our place in it. And if in a minute, and we'll be launching in about a month, it's really that photon time machine. I know that sounds like something out of Star Trek or somewhere, but that gives us the vision to see beyond. And moving into space is always about that change of vantage point. The James Webb vantage point, and give us the light, the echoes of light from different times in the universe. That is one of the ways in which science works, and it works in other ways as well. But this will give us, I think, the confidence to build both big things, the size of tennis courts, but also small things that are smarter and distributed, which is what many of you are thinking about. And for me, what's exciting about James Webb is its connection to exoplanets. And as we sit here and think of the census today, 5,000 to 6,000 exoplanets recognized, that number will be changing exponentially over the next decades as we get to understand them. And James Webb will let us actually measure the chemistry of their atmospheres around certain kinds of stars over the next decade, including ones that may be like Venus. And for the reason that we can do that using these techniques that you can see illustrated here with a transiting exoplanet in front of a parent sun or star, we'll be able to ask questions about the exovenuses that should be accessible. They may be more accessible than the bizarre and hard to find exo-Earths or super-Earths. So this is what we want to do. We want to set the stage for letting James Webb understand our sister world, which may have a story for us. And so it may be that exovenuses in different current climate states are accessible to Webb to inform us about what the ancient Venus may have been like. Think of that, looking beyond to look close by. And that's one of the hallmarks of analogies in science. And so the other thing I'd like to say is there's been a lot of talk for the last 100 years about life somewhere else. And, we're always looking for life, hopefully not in our basements or in, places like that, but out there. And while we have staggering majesty and beauty of life here on Earth, it's the life beyond that intrigues us in fiction and in science. And so 100 years ago or so, right on the cover of the New York Times, there was an article about life on Venus as the place to go. Little did they know back then about the environmental conditions of Venus, but they posited that. And today, astronomers, astrophysicists think about the clouds of Venus as a possibly habitable, a life-bearing place. Is it? How do we know? How would we know? Well, the pioneering work that we need to do is to bring the chemistry of what that environment is like to bear. The same way we're doing today on Mars with 2 US rovers, a rover also from China, and vehicles that will continue to explore Mars. So let's take a look at Venus through the lens of what we could learn. And so while we study Earth through the SmartSat capabilities that you guys will be talking about for the next couple of days, let's think of the other destinations that are in our future. Of course, the moon, humans to Mars is something that is really an excitement for many of us, having worked Mars. But then there's Venus as that destiny sister world. So how do we explore her? And the view on the left is a spectacular radar map made by the JPL Magellan mission in the 90s. And it shows us the physiography of a world that looks very different than Earth. It's a world that maybe is despun. So how do we get to know that planetary neighbor? The first thing we need to do is understand why we'd even care. I mean, in science, if we're going to solve a problem with engineering and technology, the problem has to be a good one that's relevant. And so Venus, at this time in 2021, is a very special place because her massive atmosphere can help inform us how planetary climate atmosphere systems evolve around different stars, not just our spectacular parent sun, but others that we'll be seeing and dialing up with telescopes like James Webb, like Nancy Grace Roman, like new ones that'll be developed across the world. And so those cathedrals to the skies that we extend our vision will allow us to use Venus as a special lens to ground truth those investigations of exoworlds we'll be able to see and ask, Are there environments, or were they the kind that could sustain the kinds of life, the kinds of microbiology and beyond that we know here on Earth? So Venus, if you see in the four sectors here, is really a happening place right now. And her atmosphere has not been visited by anyone in over 40 years. So it's really surprising to me, with all the great work by partner space agencies in Japan and Europe who've studied the Venus planet from orbiters recently, that we haven't looked and taken the plunge in the deep atmosphere. It's kind of like the deep ocean here on Earth that we all know and wonder about spectacularly. The deep atmosphere of Venus, the lower 60, 70,000 feet, is so underexplored that anything I would tell you today is likely to be wrong. Some of the measurements are either inexact or imprecise or just plain non-physical. And so how do we get to know a world without knowing its deep atmosphere? That would be like ignoring the troposphere of the Earth in which we live. And so we have to go there to do that. We've done that to the moon and Mars. We're going to go to Europa with Clipper. We have to do Venus, and that's the rationale for the mission that I'll be talking about, named for Leonardo da Vinci, also an acronym, which we've been competing for the last 10 years to be in this position now, ready to start developing the system. So I'm going to talk to you about Da Vinci, inspired by Leonardo, but the acronym, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, yes, it is a mouthful, is all about how to get to know Venus as a system. Because ground truthing that atmosphere by bringing the lab to the samples before we bring the samples back home to Earth is an important step. We've done that. We've done that at the moon. We've done that at Mars, and now it's Venus's time. And in the future, there will be other great worlds. Saturn, of course, going to Europa with a Europa lander. So this will be the first mission, the Da Vinci mission, that we're implementing now with our partners by the peoples of planet Earth since 1985 and the Soviet Vega landers. So that's a long time to think about it. Think of what any of you who are even alive in 85 were doing, the me decade or whatever they call the 80s. So let's take a look at the mission. The mission that we designed with engineering solutions, with technology, with also technologies to solve science problems, is all about distributing vantage points at Venus, both from flybys and an in situ spacecraft, a complete spacecraft that I like to call a flying rover that will take us into that atmosphere with our partners in industry at Lockheed Martin and across NASA, and with universities such as the University of Michigan and the Applied Physics Lab. So our mission is all about to change the game at Venus. And it starts with a prime directive. Now, some of you may not like Star Trek, and I'm a huge fan of Dune, by the way. Go see it if you like movies like that. But the big prime directive for us is, why, in the name of humanity, are Venus and Earth so divergent in their histories? The Venus we see today is nothing like Earth. It's a hellish hothouse with a runaway greenhouse atmosphere, with a day that's longer than a year in its rotation around the sun, based on its rotation, no seasons, and a very mysterious interaction of its history with its atmosphere over time. And we thought we knew something thanks to Magellan and the missions before, but there's big questions. Was Venus a habitable world like past Mars, like Earth has been for billions of years? And how did that habitability change, or was it ever? And can we understand exoplanets that are likely like Venus by understanding our own Venus? And these are tough questions. Ultimately, though, the goal is big. Can we look at Venus back in time in the context of our own world at 2 or 3 billion years ago? And some of the very special rocks in Australia bespeak to those times in the history of life that all of us in planetary sciences love to talk about, but also comparing to the ancient Mars, the cryo-ocean Mars, and Venus. If we can connect them through understanding this quest for habitability, the possible abode for life, that would be spectacular. That would connect us all as a triad of rocky planets. And the other thing is, inescapably, Venus is our exoplanet next door. Big atmosphere, infinitely sensible in the sense of telescopic remote sensing, as we look at these transiting exoplanets, the kind of thing we can learn about with James Webb and the other big space astrophysical observatories that are coming in the next decade. So that exoplanet next door allows us to look at Venus, and perhaps exovenuses in different states of evolution, looking back in time. We can't promise an exo-Earth, but we can promise an exovenus. And maybe by reading the records of the Venus we can get to today in the 20s and 30s, we can look back in time at the ancient Venuses and compare those to the exovenuses we discover and measure. And this is part of a strategy that the scientific framing organizations around the planet have been talking about for the last several years as we study exoplanets. So wouldn't it be cool, and I hope you agree, if the history of Venus was an oceanic history that rivaled the billions of years of Earth oceans that led to the springboard for life? And so current models of the possible climate history of Venus, as you can see here from Mike Way and Tony Del Genio, shown in those little the little ovals there, show Venus in temperature states that would have been adequate to support surface liquid water oceans kilometers deep, like on Earth. Now, that's not what necessarily happened. Other models can predict steamy atmospheres with no oceans. How can we try to put Venus together in the same time frame that Earth went through its massive change, its oxygenation, its microbial life force that led to who we are here today? And so Da Vinci's job is to try to measure some of those timescales by going there with the kind of instruments that today we operate on Mars, on rovers like Curiosity. And when we organize what Da Vinci's doing, and forgive the pizza look here, but it's a circular trace matrix, so just another way of explaining things. While our job is simple, we use the tools of measurements and new classes of instruments that go to new places to measure them. Chemistry that gets at history of atmospheres, change of atmospheric states, isotopic ratios, chemistry of rocks, dynamics, heat flow, putting these things together in this arrangement so we can look at evolution, composition, and history of this one ancient mountain region on Venus, not unlike places that some of you may know in Western Australia. As we look at them this way, it allows us to build the kind of mission that we think we can execute. And so our job, come June of 29, is to launch a mission that consists of multiple flight systems, a carrier relay imaging spacecraft that will carry a meter diameter spaceflight vehicle, a so-called probe, a titanium sphere full of avionics and other sensors and radio systems, to Venus. But first, flying by Venus 2 times with the new classes of instruments to measure its cloud tops, its dynamics of those clouds, and to look at the night side Venus, where we can see to the surface the glowing chemistry of the rocks. We set up our mission by flying by Venus twice to phase ourselves so we can come back to Venus and enter and descend and make our measurements over a particularly interesting place that's about half the size of Australia. So we think we can hit it. It's a pretty big place, a set of mountains that were first discovered with the first radio telescopes from Earth, like out of Arecibo. And so our mission consists of flyby remote sensing like we do for comets and other objects, with an in situ phase that requires an aeroshell, an aero entry vehicle, to go through that transition of the upper Venus atmosphere to get to the surface and collect data. And this is a complicated system in a competed mission program that we use at NASA, some of you may know. So it takes a lot of effort to win these things. Our final proposal was 1,380 pages long, plus another 1,000 pages of spreadsheets to even have a shot at this. So on behalf of our team, we're very excited. And the idea is to return 0.5 terabit of new data about Venus in a way that has not been done literally in decades. And so our mission, while it will consist of these great flybys, also is all about this excitement of an approach phase, an entry, a descent, a science phase, and a touchdown on Venus. And again, this has not happened in the history of humanity on purpose since 1985, and that's a long time ago. So we need to reinvent techniques to enter an atmosphere with 3,000 watts per meter squared entry conditions, go through lots of thermal transitions from minus 50 to 450 degrees at the surface, pressure transitions, very toxic and caustic aerosols in the clouds, parachutes to slow us down so we can do our job, and then free falling over a complex mountain system. So that's the job of Da Vinci. This one slide, which I won't belabor, is where all the action is. We have 7 instruments that will explore Venus. 5 on our probe, our descent sphere, which again is about the size of a large beach ball, but kind of like a flying descending rover, or maybe even a bathyscape. It includes 2 analytical payloads, very similar to those that have been operating for 9 years on the Curiosity rover. A mass spectrometer, quadrupole mass spectrometer, and a tunable laser spectrometer that can read the records of chemistry through samples ingested by this probe hundreds of times, parts per million to parts per billion sensitivity. So we can literally read the records of those gases the way we would in our labs. Atmospheric structure investigation to measure all the environments, a descent imaging system with a eyes wide open approach to see that planet as we come out of the clouds and hazes, and to see that surface of Venus in a way that we can't see from above the clouds, which are so opaque they blur out the infrared and visible and allow radar to only go so far. And also to carry the brainchild of students to the surface, an oxygen fugacity sensor to see the state of oxygen right near the surface, which will influence the rocks. And meanwhile, our carrier relay spacecraft will carry an array of cameras and a new ultra-sensitive hyperspectral imaging spectrometer for the ultraviolet to look for mystery absorbers in the upper atmosphere and motions of clouds, which we think are coupled to the climate history. All of this in the budget of a blockbuster movie is our job. And there's a lot of key innovations in engineering to make this possible. And our engineering team has been brilliant. So what are we going to do? We're going to answer the questions on the left. And I'm not going to read through this traceability, but to say those are the questions that have been around since the 80s. What is the origin of the big Venus atmosphere? Is it a new one? Was it accreted that way? Did it degas from volcanism? Was it seeded by comets? What is the pace or the situation with the role of water on Venus? Were there surface oceans or steamy atmospheres or both? Were there never any, even though there's a lot of water vapor now in the Venus atmosphere? And what about these weird mountain systems that look ridge-like things you see in the seafloor and maybe in the relic mountains, some of the exhumed mountains like you have in Western Australia? What are they? They're not like anything we've seen on Mars or the Moon or Europa. What are they? So we've traced our job from those questions through our instruments and the measurement sensitivities and frequency and style we need to address those questions with these 7 instruments. And so we hope this mission will be a people's mission to Venus, engaging everyone from people interested in images to spectroscopy to chemistry. And, if I were going to give you one catchphrase, it's all about the chemistry, folks. If you didn't like chemistry in high school, well, this may not be the mission for you, but we need to do the chemistry at Venus so we can get to the next step. And so our mission, launching in 29, will emplace a probe flight system to Venus. And inside that probe is not just an inert, sphere, but it's actually a complete smart spacecraft, like you're talking about at your conference. Avionics, 2-way RF telecommunication, and with a transceiver that does an adjustable data rate as we descend with our parent spacecraft. Phase change materials to buffer the temperature changes. 5 instruments plus an entry system experiment to understand the entry conditions. Parachutes, spin vanes to stabilize us for our imaging. All of a couple hundred kilos that will last about an hour through its transect through the Venus atmosphere. And its fate at landing is unknown. We do not require landing. In some ways, this spacecraft is a landerless lander because we expect our final images to have resolutions in the tens of centimeters in multiple wavelengths. So we can use them as if you were bringing your favorite family drone home after a vacation and landing it in your backyard. And so this is our vehicle, a lot of innovations in this to allow all this to happen to the planet Venus. And our flight trajectory is an interesting one. We enter and deploy our spacecraft through its aeroshell. We jettison that at around 70 kilometers and inflate a parachute, a disc gap band parachute that allows us to hover a little bit more in the middle atmosphere where the clouds are, where it's cooler, but full of aerosols to make measurements, special ingests, and then once we get to the lower cloud deck and the haze layer, to free fall all the way to the surface. It's somewhere between 13 and 11 meters per second. That's about the speed of driving your car into a tree at about 20 odd miles an hour. Not recommending that, by the way. The vehicle on the left is our test unit that we tested on this profile during COVID. And so we are confident we can do this profile and make those measurements. And ultimately, as we explore Venus in this very fast transect of this spectacular atmosphere, we'll be making measurements through different layers, asking different questions. And we'll be relaying those to our overflying spacecraft, which will be in a relay mode, the Carrier Relay Imaging spacecraft developed by Lockheed Martin, as we do this during a period of about an hour and 10 minutes. And we'll study the upper cloud deck and the chemistry, particularly of sulfur species, oxygen, the heavy to light hydrogen in water vapor. Well, as we get into the atmosphere, we'll ingest samples and measure the noble or inert gases. Very important because they tell the story back in time. As we emerge from the clouds, we'll start imaging in the context of chemistry, looking at the surface from 60, 70,000 feet all the way down at the scale that will allow us to start making measurements that we're used to for Earth from satellites like Landsat and Sentinel, RadarSat, and below the clouds, increasing the cadence of our measurements of chemistry of trace gases. We don't even know what might exist down there, but we'll be measuring and scanning for many ones through a wide range of Daltons to look for those. And then finally, as we get close to the surface, looking for gradients, disequilibrium chemistry of the rocks and the Venus air. In fact, the lower 10 kilometers of Venus atmosphere is likely supercritical carbon dioxide. That means it behaves more like a fluid than a gas, and those interactions are unknown. They may be affecting the alteration pattern and erosion of these rocks in the mountains especially. So we want to get to know that, and ultimately, as we land, bringing images down at sub-meter scale that will show us the nature of the landscape in 3D. So these are the things we will do. These mimic but extend the things done on the Huygens probe to Titan, but now with 21st century instruments. And so what are the questions? And you might be thinking, okay, this is all great, but how are they going to answer anything with all these numbers? Well, the big one that all of us care about is the role of water, this magic, universal solvent. Its role on Venus is important because there's a lot of water vapor in the Venus atmosphere, as best we know, sensed from remote sensing and in situ probes. So how do we tell? We look for the history of water through these lenses of atmospheric origins, delivery of the gases and the volatiles, how degassing has worked over time, and how losses occur. We need to look at the balance between the sources and sinks, as we're doing at Mars, as we do at Earth for Venus. And we do that through these tricks. These are the ways it work. We look at the inert gases and their isotopic ratios, their abundances, their distribution in space from the top of the atmosphere down for species like deuterium and hydrogen and water. Those are the variables that work. And when we do that at Venus, we'll make those measurements from below the homopause in the entire Venus atmosphere. And that's important. We can only go so far with telescopes and flybys and orbiters. We have to get into the atmosphere to see the action, the same way the rovers had to get to Mars to see what the rock record can tell us, as Perseverance is doing so well today. And so one of the keys is xenon, the heaviest of the inert gases, the nobles. The ratios of the xenon isotopes is critical, and we just don't know what they're doing on Venus. And that will tell us whether Venus evolution of its atmosphere is more Earth-like or Mars-like or different. And then as we continue our descent with this probe in its hour-long, roving of the atmosphere, we will sample the atmosphere every 100 meters or so through the window of many different trace gases, often those involving sulfur, hydrogen, oxygen, carbon, phosphorus, and nitrogen. And we'll do those with very high time rate measurements, every 100 or 200 meters. By measuring that often, we'll look for chemical gradients that tell us about the chemistry and the workings of that atmosphere. We'll look to see if the ratio of heavy to light hydrogen changes with altitude. There's some hint that it might, but we don't know, which could reflect totally different history of water in the deep atmosphere versus the upper atmosphere, and look for other molecules, including the mystery molecule phosphine that has been perhaps detected from space-based, from Earth-based observatories like ALMA and James Clerk Maxwell. We can actually measure that kind of species down to parts per million or better in the atmosphere itself. And so this will give us the ability to make, and I hope you all memorize this, the wiring diagram, that was a joke, folks, a wiring diagram for the kind of chemistry that could exist on Venus if things work the way they think they do. This is just the putative oxygen cycle, because oxygen in the history of planets is important. It can also lead to false or misunderstanding of what generates that oxygen, which some people use as a biosignature, a source of signs of life. So if we see oxygen in atmospheres of exoplanets, is that signs of life or habitability or something else? Pathways from chemistry, volcanism, and others. So we need to separate that out. what makes these pathways. No one's done that. So if we don't do that, we can't get to the next question, which is, could Venus be habitable? Was it inhabited? What is the astrobiology of Venus? So we need to bring the instruments to the gas samples and measure them there, the way Curiosity's been doing on Mars. And then we come down to the rocks. Now, I'm a geologist. I like the rocks. I hope you all like the rocks. There's great rocks in Australia, by the way. Love them dearly. And so as we look at planets, there's the simple rocks, the lava rocks, the basalts that form and erupt and cover ocean floors or lunar mare or plains of Mars, like the northern plains. And then there's the more evolved rocks that involve interactions as they're made with things like water, that are the hallmark of the continental cratons on Earth, as you have in Australia, in Canada, in Russia, and in South Africa. And these cratonic regions have a long history of early crustal genesis involving water in the making of rocks. And we call often those rocks granites, granitoids, and they're special. They're from a past epoch. And they're important too, of course, on Earth. How can we look for those on Venus? Through an atmosphere that's 40 kilometers of clouds and very difficult. Well, we can look at some things from as we fly by, but we need to go there to do that. So we've picked a place on Venus. It's about half the size of Australia, known as Alpha Regio. Now you might say Alpha, why isn't it called, some famous name for some great woman scientist? And it should have been, but Alpha was discovered from Earth-based radio telescopes back in the 60s, and it was one of the first 3 places named as Venus was explored, including from Arecibo. And so Alpha, here shown on the left, is an area with ridged mountains that rise up to 10,000 feet. It's a continent. So we're going to go and zero in, coming in over Alpha at the highest solar elevation we can, and open our camera eyes to Alpha from roughly a height of around 100,000 feet all the way to the surface, acquiring up to 500 images as we descend in multiple wavelengths to enable us to look for signs of chemistry of rocks. And it turns out that the difference between those basalts and those granites can be easily separated if we collect just a few bands of data often enough and put them together. And so that's what we're going to try on Venus. It works on Earth. In fact, we've tested it. If we look at the rocks of, in fact, the Pilbara Range in Western Australia, through the same wavelengths we will be looking at Venus, what do we see? We can tell the difference between the ancient granitic rocks, the felsic rocks, shown in the panels to the right, and those that are not. So we can distinguish at the scales we will see on descent over the mountains of Venus using this test case that we've developed from the famous and very astrobiologically relevant rocks of the Western Australia Pilbara region. We can actually do this kind of work at Venus. That's spectacular. That means we have the prospects of finding rocks that must have been made in the presence of water, and that would tell us that perhaps these ancient continents, if the result is we think, are a relic of a time on Venus when there may have been more water involved in the making of crust. And we don't know that that's the case, and we can look for that above the clouds, but we're going to go below the clouds and make measurements at the scales we're used to making for Earth, as you can see in these images, for Venus, and that's pretty spectacular. Ultimately, our job is to try to connect the history of water and habitable environments on Venus through time. And there's different ways that can work. You can see Mars, Earth, and Venus here, and the different tales of things that could happen. Lots of volcanism, producing water vapor, liquid water as oceans in the history of the planet, conditions for life involving that liquid water, and other protective environments that could occur. And for Earth, we understand those. They're spectacular. For Mars, we're becoming understanding of at least some of them. And they may be episodic. They may be colored by climate change. That's episodic, where the freeze out, become small lakes, dry up, and then repopulate. But for Venus, we don't know. Some models predict Venus may have been an oceanic planet for billions of years, and others say, no way, that could not have happened. So how do we tell? We need the chemical measurements from Da Vinci to put things into order. And that's the job of our mission ultimately. And so we know on Earth that the history of Earth is not just the history of one simple planet. It's a history of time epochs in which different things happened, oxygenation phases, history of microbial life, transitioning into the kind of life that we are. That's the history of Earth. You can see the names of our famous eras, and they're really well represented across our planet, Many of them, by the way, from very unique fauna and flora in Australia, which is very special to me. I'm interested in that stuff. But what if Venus had a long habitable period that lets us look at Venus in this way too? Could we tell? Well, if we can tell that, Venus is going to become an even hotter place. As much as Mars is way cool, really, Venus could be way hot, and way hot in terms of science. So our job with Da Vinci is to bring a spacecraft flight system to the planet and ask questions that involve these kind of measurements: surface composition of rocks in the atmosphere, noble gases and their isotopes, through the atmosphere at the scale that matters, scale we know works, ratios of key species that are in water, like heavy to light hydrogen, that tells us how much water was there, how much was lost, and maybe when it was lost. We put all those pieces together, as we've done at places like Mars and Earth. We can see the history. That will be spectacular. And we can combine that with other missions that have been recently selected by NASA in Europe that will take other powerful remote sensing techniques, the state of the art, to Venus. And so for me, that's important, but there's another story, because our Venus is really an exoplanet next door. Without understanding our Venus, understanding the exovenuses that James Webb is sure to see will be incomplete. So we can use our Venus and what we measure with Da Vinci and these other missions to inform and instruct the observations of James Webb and these next generation telescopes that have just been discussed in a recent National Academy report in the United States called Astro 2020. Just imagine by the 2040s, telescopes that can actually image exoplanets within around some kinds of suns. These are possibilities. And so we need to know our Venus so that we don't misinterpret what we see. And so knowing our Venus will let us see whether there are other Venuses out there and how they work in time. So come about a decade from now, we will be on Venus again. The people of this planet will have landed, and we will have learned, and that data will be available for everyone. But there's a bigger job. These scales are important, but the trick and what your conference is all about is how do we make that happen? Because vision is great, but execution is everything. I think a famous inventor once said that. Da Vinci was like that too. So we need the flight systems that can do this job, that are affordable, low enough in risk that we can ensure they'll happen. And that's our job on Da Vinci, to build the team with our partners, such as the colleagues in Lockheed Martin you see on left, with a simulation of our carrier relay imaging spacecraft. The scale there is about 9 feet tall, about 8 feet wide. And our probe flight system, or descent sphere you see on the right, it's colored that way because the titanium vessel was actually charred in its excursion to 460 degrees C several months ago when we did the tests. So we need to put these flight systems together in the 21st century way so they can explore and uncover the new Venus. And looking inside that probe, make this probe flight system the smart probe. Just like you have your smart satellites, we need the smart probes to look at not only Venus, but Saturn, Uranus, Neptune, all those places where this kind of atmosphere imaging flight system makes sense. And we haven't done that kind of thing since really well, since the 80s and 90s. And so now we're ready to take it back to these other underexplored worlds. And that's our job with Da Vinci, to bring this technology to Venus so that the girls and boys out there interested can open the doorways to using Venus as we've used Mars and the moon to understand our place in the solar system. And that's special. The moon rocks we look at today still tell those great stories. The ones we bring back when the women go to the moon, even more. Well, those girls and boys who are thinking about exploring space, Venus, I think, will be a doorway for them to see what might have been and what a destiny could be. So we think that's very special. So as I conclude, I want to remind you that ultimately Venus may be telling us about this livable environment, this habitability as a process, so we can interpret what we see way beyond our solar system, because we're not alone as planets in this universe. And there's probably countably infinite planets around these suns that we'll get to know with James Webb and other great telescopes. But the habitability question links it to us here on our spaceship Earth. So I'd like to finish with a little movie. I'm going to play a movie about our mission. We call it Da Vinci, the movie. And so please enjoy for the next 2 minutes, and then I'll come back. Hopefully everyone
Launching
can
in
hear.
2029, the Da Vinci mission, named after Leonardo da Vinci, is designed to address fundamental questions about the origin, evolution, and composition of Venus. During 2 gravity-assist flybys, Da Vinci will study the cloud tops in ultraviolet light, tracking cloud patterns as they change with time and analyzing signatures of mysterious chemicals that absorb ultraviolet light. Both flybys will also examine heat emanating from the Venus surface on the planet's night side. We will look for geological clues of this planet's mysterious past to paint a global picture of surface composition and the evolution of the planet's ancient highlands. 7 months after our second flyby, Da Vinci will release its atmospheric descent probe. The spacecraft will watch its probe enter Venus's atmosphere over the course of 2 days. The probe will take about an hour to fall through the atmosphere, taking measurements and snapping images down to the surface. These measurements include profiles of composition, winds, temperature, pressure, and acceleration. Key gases will be measured to help us understand how Venus formed and evolved. Some of these measurements may reveal chemical signatures of ancient water. With our suite of measurements, Da Vinci will provide new insights into Venus's atmosphere's complex composition, structure, and chemistry. As the probe nears the surface, its descent camera will capture breathtaking bird's-eye views of the mysterious terrain known as the Alpha Regio Tesserae, possibly revealing that water once flowed across the Venusian surface. These up-close images of the surface will provide new insights into geologic processes and will help us to understand what it might be like to stand on the Venus surface. An oxygen-sensing student collaboration experiment will shed light on the role of this gas in the Venus atmosphere. The discoveries that emerge from this diverse dataset will tell us whether Venus was truly habitable, and the story we reveal at Venus will reach even beyond the solar system to analog exoplanets that will be observed with the James Webb Space Telescope. Venus is waiting for us all, ready to take us there and ignite a new Venus renaissance.
Our 2 deputy principal investigators, Judd Arnedy, is really just a synopsis of what we're trying to do at our sister world. And this has been a dream of mine and many of us on our team, it's several hundred women and men, as we've tried to navigate the competitions to have the opportunity to fly this kind of mission. And so we're looking forward to this and to take the legacy of Leonardo and his visionary engineering and science and technology and art with us to Venus as people. And so at this exciting time, I think Venus will become the hot place as we continue to explore our solar system and connect it beyond. We think Da Vinci will be one of the pieces of the puzzle to bring it to everyone, and the engineering solutions that give us this Da Vinci will be extraordinary. So I wanted to thank you all for your time and stop the presentation and take questions. Thank you, everyone.
That was brilliant, Jim. Absolutely brilliant. I won't clap in the interest of all of our ears and the headphones we're wearing, but if we were in a room together, that would be just brilliant. It's excellent. I learned a lot in that, to be honest. And you know, one of the key takeaways, I think, or a couple of takeaways I took from here, is the tie-in to JWST, which I think is brilliant, and we're looking to the future there. That's just great. I'm going to open this up to questions. Viewers here can throw questions. Sasha has already thrown a couple in that have been answered. Please don't hesitate. While we wait for that, I've got a couple that I'm going to throw out there at you, if I may, Jim. You know, you touched on a handful of things, you know, and I think one of your key opening statements was that tech empowers the science of the future, and that's brilliant. That's, I think, what we're all here trying to do, and a big role of SmartSat CRC. Can I touch upon this? You know, Venus, you've been working on Venus Explorer concepts and ideas and trying to get the mission going for a long time now. And it's faced perhaps political, competitive, even, you know, financial distribution limitations. But has that given you the opportunity to now work on the technology and the R&D development to effectively now enable more and better science and data over these past decades, for instance? And can you comment on that, and perhaps any specific R&D or tech that's really advanced in that time frame to now enable more from this mission?
Well, Andrew, exactly. And thank you for asking that question. Our engineering support team, and I'm just, a science guy, with our science team. So forgive me. I respect what we've been able to do over the last 12 years as we've been competing this mission repeatedly. It's like building a castle in the swamp. It sinks, you build it again. That was a little joke. But anyway, by reinvesting the technology to imagine spacecraft that are smart enough to react and operate very sensitive instruments like we normally have in our labs in a very unfriendly environment, by changing the environment around them. In fact, our spacecraft is really like a cocoon that gives the sensitive mass spectrometers that love working on Mars, on Curiosity and Perseverance, they'll do great on Europa, give them the environment to which they can work. And so what we've been able to do is innovate sampling systems so we can bring gases frequently into instruments without clogging inlets. That was a big problem back in the 70s. When the first forays to Venus went, we can also provide phase change material thermal systems that allow us to transition from temperatures of -50 to +450 in an hour and still be a working flight system that will allow us to perform. We've changed the way we do imaging. We're not just imaging to take black and white stills. They're great. We're doing multi-phase near-infrared images so we can construct topographic maps using structure from motion imaging with very low baseline geometry. It works like a charm. In fact, we've tested it on the new island in Tonga called Hunga Tonga Hunga Pai. Worked like a charm. Students did it with a drone. It's fabulous. So we'll be using that at Venus. And we've tested that method as we landed Curiosity on Mars in 2012. So we can actually produce three-dimensional renderings, the great buildings in Italy that Da Vinci thought about, by using this technique. And we hope that this kind of technology will be implementable in FPGAs and other technology solutions where it can be done on the fly. And so we could literally bring spacecraft that don't send back 10,000 images, they send back a point cloud of the solution. And likewise, our spectrometer that will fly by Venus twice will use a machine learning technique to take the 0.2 nanometer spectra and machine learn to send back, quote unquote, the minimized retrieved spectra that we think will tell us about the chemistry of that atmosphere. And that'll be the first ML hyperspectral imaging spectrometer experiment at Venus in history. So your question, Andrew, which is so good, is that we've had the time to innovate. And I think all the missions that are going to Venus are going to be doing that. In our case, it's the flight systems. Our camera systems will be using night side infrared imaging with framing cameras, not a spectrometer, to measure composition using particular wavelengths of light. And this innovation means we can do it simpler and not have to have very expensive, big, $50 million spectrometers. But a framing camera like that we use for navigation can still do chemistry. So we've attempted to innovate. Our student collaboration experiment literally comes right out of the industry that looks at high temperature reactions as people test race cars and things like that. So we'll be using that technology to measure the partial pressure of oxygen. So the time has benefited our technology engineering solutions to let us be able to do this mission. Now, the flagship missions, the frontier missions like Webb, they use time as an integration tool to build the capability that didn't exist. We've very creatively used engineering solutions that we knew we could integrate to solve the problem rather than having to reinvent all of them to do this class of mission. Future missions to Venus may have to invent and should invent long-lived high temperature technologies that are now in discussion, as you know. So this has been one of the things that's really helped us, I think, do this mission.
Fantastic. Yeah, thank you, Jim. I appreciate that. We have a couple of questions coming in here from our audience, and I'll shape this. Thank you to Sasha and Gerald here. I'm going to combine this into one, and it's really focused around the comms and the comms link from the probe back to the orbiter. Can you comment there on exactly both the technology that's being used? I'm assuming that's all radio frequency, and what sort of relay and data rates that we should be expecting as part of that comm link. Can you comment on that, Jim?
Yeah, so we have an S-band link, and the transmissivity of S-band at around 2.5 gigahertz through the Venus atmosphere is well known. We've used it to look at Venus from Earth radio telescopes. The Magellan mission used it in the 90s to map Venus, and it's been the hallmark of two-way transmission through the atmosphere of Venus from probes since the first successful Soviet probe, Venera 7. So we know that works. So we're using S-band, maybe a little non-traditional relative to the the XKA bands that are so common in RF. We have an adjustable data rate radio link that we will use as a two-way transceiver for our overflying spacecraft at distances on the range of 5,000 to 10,000 kilometers. As they listen to our probe, they will dial up and down the signal strength, the data rate, so we can get more or less data back. If anything goes wrong, that solution, which is a radio developed by Johns Hopkins University Applied Physics Lab, which will be flying also on other spacecraft, and which was tested on Messenger to Mercury, will fall back to a fixed data rate. So we won't lose anything, but by allowing us to adjust those final data rates as we near the surface, will be optimized to get way over 100 kilobits a second, so we get more images back. And while we're looking at our images in an information theoretic measurement system to decide if they have enough information content to be prioritized, this new data rate will get us up as high as a megabit a second in a two-way link between our flyby spacecraft, the carrier relay imaging system, and the probe. And that'll allow us to get more data. Our mass spectrometer collects a lot of spectra, and if it's doing so every 50 meters as we get close to the surface, we need to get those back. And so this will allow us the luxury of ensuring we get a minimum amount of data back, but at a maximum we get a lot more. Our potential on this mission is 500 descent images. A few times ago when we proposed, we were talking about 30. So we're talking about 30 images versus 500. And so that'll be a big difference as we go. So that technology we feel is ready to be used at Venus. It could be used at Saturn and other worlds, and allows for a smarter solution. Again, using S-band, we have a 2-meter high gain S-band radio on the carrier relay imaging spacecraft to talk to the probe as we transect the atmosphere. So we're very excited about that. It's a new wrinkle and a great engineering solution for us that our team has put together with our project system engineer and team.
Brilliant. Thanks, Jim. That answers that. That's great. We have one last question here, Jim, because we are coming short on time, and see if this one's a quick one for you. But there's a model right now for the water that's on Earth is it coming from rich asteroids in the solar system. Is that the same approach for Venus and the history of Venus? Can you comment on that?
Absolutely. So the early capture of water as a volatile input to a planet is very important. And by looking at the ratio of the isotopes of the noble gases, we can tell which model probably was most important at Venus relative to Earth. And so while we have the inert gas ratios for Earth and for Mars and for the solar wind and for Jupiter, we don't have them for Venus. So we think we understand those other worlds and what happened with early Mars versus early Earth. We don't know early Venus. Was it Earth-like? Was it not? Was Venus' strange rotation an inhibitor to that kind of capture? So we need to look at that very carefully, because Venus and Earth are both in this what should be very similar inner solar system zone post-accretion. So that's a key question that we'd like to address with our mass spectrometer measurements, and we believe we can. I hope that answers the question. Sorry about my long answers. Get a little excited here.
Oh, Jim, we're eating it up. This is great. I am, at least. This is excellent. Well, Jim, I want to thank you again on behalf of all of us here. This has just been fantastic. It's a great way to start off our conference. This is just wonderful what you're doing with Da Vinci. To be honest, congratulations on the mission. It's wonderful to see Venus back in the spotlight. I think it's not only just great for the exploration of the solar system and for the advancement of tech, the partnership, like you said, between industry and NASA here to deliver on this and ultimately execute is so vital and important. But I think it's also key, and this is something you brought upon, which is important to me, which is what this does to inspire that next generation. And even just getting those images from the surface are going to do so much for all of us on the way down. And that to me has such an impression and such an impact. So it's wonderful. Thank you. I very much appreciate it. Well done. Congratulations. And thank you so much, Jim. I appreciate it.
Thanks for having me, guys. Have a great conference, and can't wait to visit someday. Hope everyone's well. Thanks again. Bye, Andrew.
Thank you, Carl. Thank you, Jim. Fantastic talk and presentation. Wonderful to be able to have Jim with us today and be able to share such insights with us around the Da Vinci mission. Thanks, Carl, for that session. We'll now have a short 20-minute break before our next session commences. We will run a tight ship and we will keep to time. Please check the lobby for the session details. It is presented in your local time. Take a minute to refresh that coffee cup, consider a poster or two, and we'll see you back in 20 minutes for the next session around the Aurora Space Cluster. Thank you very much.